morning friends, I welcome you all for another lecture on the course Microprocessors and Microcontrollers. In today's class, I am going to discuss about the topic PIC 16C61/71 microcontroller timers. We know that each and every microcontroller, most of your microcontrollers have a timer/counter circuits. Those are act as a timer as well as a counter. In both the cases, what they are actually doing is they are counting the input clock pulses. So coming to PIC 16C61/71 microcontrollers, there is one 8-bit timer circuit which is called timer 0 along with one watchdog timer WDT. I am going to discuss about these two things somewhat in detail in this lecture. Right, my first point is PIC 16C61/71 microcontroller has one 8-bit timer along with watchdog timer WDT. And coming to my second point, the timer in these controllers are 8-bit. That is a timer 0. So it is a 8-bit timer which is timer 0. So I am going to discuss about the timer 0 in somewhat detail. Timer 0. The clocking source for timer 0 can either be the internal system clock or an external clock. That means this timer 0 get the clock signals from internal oscillator circuit. The oscillator circuit generated clock signal passes through a divided by 4. That means each and every machine cycle consists of 4 clock cycles in PIC controllers. That's why here the internal oscillator circuit produces clock signal passes through a divided by 4. So that here the timer 0 get the clock signal from internal oscillator circuit, that is number 1, or it may receive the clock signal from external, that is called external clock. Next, the external clock to timer 0 can be given at a port A signal, that is RA4, which is called as TOCKI. That means a timer 0 clock input. So that is next, timer 0 overflows from 0FFH to 00H. Then what happens is a flag in INT-CON which is called TOIF, means a timer 0 overflow interrupter flag is set to 1. That means whatever the timer we are identifying in this PIC, that is a timer 0, always do up counting. That means always once it receives the input clock pulse, the content of timer increments, so that there is a chance the content of this timer 0 value reaches to FFH. That means all 8 bits of timer 0 is equal to 1. The time it receives one more new clock pulse, what happens is its content is rolls off from FFH, that is all ones, to 00H, that means all zeros H. This is an information provided by this timer 0 by activation of a flag in INT-CON, that is called timer 0 overflow interrupt flag. So that is the meaning of this. And next, it causes an interrupt if the timer 0 interrupt is enabled, that is if T0IF along with GIE bit in INT-CON are also set. So here important thing is, in order to consider the timer 0 generated interrupt, in order to process it, we have to go and set the bit, that is a T0, not this is IF, it is IE along with GIE bit. What is the T0? So TOIE. TOIE is nothing but timer 0 overflow interrupt enable bit. It is a control bit. With the help of this bit, we can enable or disable timer 0 generates overflow interrupt. If that interrupt is considered by the controller only when this bit is set to 1. Not only this, along with this, one more bit, that is a GIE, means global interrupt enable bit, that is also set. Then and only timer 0 generated overflow interrupt can be considered by the controller. Otherwise, it can't consider it. See here friends, for example, this is the scenario. So these are two are given to an AND gate. One is the TOIF, that is a timer zero overflow flag. And next one is the TOIE, that is a timer zero overflow interrupt enable bit. If these are two are set to 1, the output of AND gate is 1. And along with this, one more input, that is a GIE, that means a global interrupt enable. This is also set to 1. Then and only the interrupt can be considered by the controller. That's it. So either of this, that is a TOIE or GIE, any one of these two bits are set to 0. What happens is the timer 0 generate overflow interrupt can't considered by the controller itself. That is the important thing here is. In case of external clock at RA4, which is a alternate function is a TOCKI timer 0 clock input pin. Timer 0 module can configure to increment on either rising edge or falling edge. That means your timer 0 consider the external clock based on the triggering notation, that is, it will consider the clock either rising edge of the clock or at falling edge of the clock at the pin RA4 whose alternate function is timer 0 clock input, that is a TOCKI. So that's the meaning of this. Timer 0 has a programmable prescaler option. That is very important, friends. This is a timer 0 have programmable prescaler option. That means by using your 8-bit timer, it can count the maximum counts of 256 because 2 power 8 is equal to 256. Let you can assume to count one clock pulse it will take 1 second. To count to 256 clock pulses it takes 256 seconds. But if you want to make a more time delay with the help of a timer 0 of size 8 bits without increasing its size, then what we are doing is we took the help of this prescaler circuits. That means your timer 0 have a provision, that is it may support a programmable prescaler option. Basically it is used to increase the time delays produced by your timer 0 by selection of appropriate prescaling values without changing the size of timer itself. So that's the meaning of that. So this prescaling we do with the help of a least significant nibble of bits in option register. In option register, the least significant 4 bits, those are, one is a PSA bit, that is a prescaler assignment bit. Along with, we have a bits, that is a PS2, PS1 and PS0. These are 4 are least significant 4 bits of option register. With the help of them, I can prescale this timer 0. So first of all, I would like to discuss about a bit PSA, means a prescale assignment. Bit PSA in option register decides the assignment of prescaling to either Watchdog timer or to our timer 0. That means it is very clear, friends. What are the timers? Your PIC 16/61/71/71 has 2 timers. One is timer 0 and another one is Watchdog timer WDT. Both supports programmable prescaling option that we can program with the help of a least significant nibble of our option register. So with the help of a PSA prescaler assignment bit, by using this, first I decide I am going to assign a prescaling for either Watchdog timer WDT or to the timer 0. That prescaling do with the help of the remaining bits which are present in the least significant nibble of option register. One is a PS2, another one is a PS1, and last one is PS0. That I am going to discuss next. So coming to this, the bits PS2, PS1 and PS0 determines prescaler value. That's what I am saying. Basically these are 3 are present in, see here friends, that is the least significant 3 bits. This is my option register for prescaling of timer 0 as well as Watchdog timer. I took the help of least significant nibble of option register. That is a PSA, PS2, PS1 and PS0. By using PSA, I decides my prescaling is assigned to Watchdog timer or it is assigned to timer 0. With the help of PS2, PS1 and PS0, I am going to select the required prescaling factor. So that's the programmable prescaling of timer 0 allows handling longer interval events with the help of only 8-bit maximum value of timer count. That's what I am saying. Without a changing of a size of your timer size is still it is an 8-bit. But in order to increase the time delay produced by the timer, no doubt a prescaler is very useful for me. So that's why here what I mentioned is programmable prescaling of timer 0 allows handling longer interval events with the help of only 8-bit maximum value of a timer count. I won't change the count value present in a timer. It was an 8-bit only, but in order to increase time delays, or I can to rise longer time delays, definitely I took the help of this prescaling factor. So see here friends, how I can go and use this PSA bit as well as PS2, PS1 and PS0 of my option register to assign the prescaling for the timer 0 as well as Watchdog timer WDT. First, I start with the PSA. PSA means a prescaler assignment bit. So, prescaler assignment bit. So, this is. If this bit is equal to 0, we are assigning prescaling for RTCC, means real time clock counter. It is nothing but our timer itself, timer 0. If it is equal to 1, then we are assigning the prescaling to our Watchdog timer WDT. So this will decide we are assigning a prescaling to either our timer 0 or to Watchdog timer WDT. That's it. Next, PS2, PS1 and PS0. These are the PS represents prescaler. Prescaler bits. There are 3 bits. Then obviously I was getting 80 different combinations. These are the 8 combinations. I start from 0, 0, 0 to 1, 1, 1. So these are the different prescaling values for timer 0 as well as Watchdog timer W. So I'll tell you what's the meaning of this. So 1:2. If PS2, PS1, PS0 is equal to 0, 0, 0, then my timer 0 prescaling value is 1:2. What's the meaning of this? The meaning of this one is for receiving of every 2 clock pulses, the count value of timer 0 increment by 1. I repeat my statement. By receiving of every 2 clock pulses, the timer 0 content increment by 1. If I assign this a prescaling for RTCC, that is nothing but a timer 0. For the same combination of PS2, PS1 and PS0, if I select WDT is my timer, then my prescaling is 1:1. That means if I receive 1 clock pulse by Watchdog timer WDT, its content was incremented by 1 itself. And coming to the next combination 001 on PS2, PS1 and PS0, if this is a prescaling bits values, the time if I make PSC is equal to 0, then the prescaling is assigned to the timer 0, the time I was selects 1:4. That means if I receive the 4 clock pulses as an input to my timer 0, then its content is incremented by 1. For the same combination, the scenario of Watchdog timer is if it receives successfully 2 clock pulses, then the content of Watchdog timer is incremented by 1. So we know that guys, generally by using an 8-bit counter, it will count maximum 256. So if it is scenario 1:2, that means actually it will count 2 into 256. For 512 clock pulses, it will count it. If I go for next, that is a 256 into 4, 1024 clock pulses, it will count. I won't change the size of timer itself. The timer size still, it was an 8-bit, but with the help of this prescaling, I can increase the delay produced by the timer itself by counting of clock pulses. It won't increment the counting of a clock pulse, so it won't increment the count value based on receiving of a clock pulse. For every clock pulse, it can't increment its value. Its value increments based on prescaling values, how many clock pulses it receives. So based on that, it will increment its value by 1. That's the meaning of this. If I go for the last one, that is PS2, PS1 and PS0 is equal to 1, 1, 1. If I select timer 0 for my operation, my prescaling factor is 1:256. That means only one time the content of timer 0 was increments when it receives successfully 256 clock pulses. Once it receives successfully 256 clock pulses, then and only content is incremented by 1. So that means in this scenario, my timer 0 can count the total number of clock pulses are 256 into 256, which is equal to 65,536. That means it will go and count total 64k clock pulses. Still in that case also, my timer 0 size is 8-bit itself. I can't further increase it. So similar case for a Watchdog timer, 1:128. That means Watchdog timer content increment by 1 once it successfully receives 128 clock pulses. That is 128 clock pulses. That means again Watchdog timer size also 8-bit. 8-bit means 256 into again 128. It is equal to 32k clock pulses. So like this, without increasing the size of your timer 0 as well as Watchdog timer, I can increase the time delays by utilizing of this Prescaler option. So that is a beautiful which was present in this PIC controllers. Next, the formula how we are calculating time delay as well as how we are loading a preloaded value into our timer according to our required amount of delay, because our timers are only do upward counting. So see here friends, for example, if you want to the time delay, for example, I want to make some 5 seconds time delay or 50 seconds time delay or 5 microseconds time delay. That's the delay is how much you needed. So the delay we are calculating like this: the count value present in a timer into Prescaler value into 4 by f oscillator frequency. By using this simple relation, I can calculate my time delay. So I know what my right now count value present in a timer 0 or Watchdog timer. The time what is a prescaling value. So then both are multiplied and result is multiplied with 4 by f oscillator. So that way produces the time delay. And similarly time 0 preload count, it is a calculated as of this. So that is a 256, that is a maximum count that we can store in our timer itself, minus time delay into f oscillator by Prescaler into 4. By using these two relations, I can calculate the time delay as well as the preloaded value, how much I have to go and store in my counter before applying the clock pulses in order to produce the required amount of time delay. These two are important relations for us. And next, coming to the next thing is Watchdog timer WDT. The WDT prevents processor from endless loop. It is one of the beautiful features that was present in PIC controllers. We didn't identify this feature in 8051 microcontroller. The main job of this Watchdog timer is it prevents our controller from endless loops. That means once our controller is entered into endless loop, it was unable to come out from that loop automatically. Only the option is you have to switch off and again switch on it. That is only the option. Without switch off and switch on your controller, once your controller have a Watchdog timer, it will protect our controller from that endless loop. So that how it will do it, that will go and learn by observing the following points. The WDT will reset the PIC controller if CLR WDT instruction is not executed periodically. So here was this, our Watchdog timer will reset our PIC controller. When it resets the PIC controller, whenever it was unable to execute an instruction CLR WDT in regular time intervals, it will execute regular time interval CLR WDT instruction. That means the operation of controller is okay. There is no problem in it. Whenever it was unable to execute the instruction CLR WDT instruction periodically, that sense our controller is in some rescue condition. It may endorse into some endless loop. To come out from that, what your controller can do is, it will, this Watchdog timer, what it do is, it will generate a reset signal. Once it sends a reset signal, then it is come out from it. That's the meaning of this. The CLR WDT instruction. What this? CLR WDT means clear Watchdog timer instruction sets the time out bit, that is a TO bar, which was present in status register. What this CLR-WDT can do? CLR-WDT instruction sets timeout bit. Timeout bit, this is generally at low signal. It initially what it does, it makes 0. It sets in the sense that TO bar is equivalent to 0. So this execution of CLR-WDT instruction makes a timeout bit which was present in the status register, which is a TO bar is equal to 0. It can turn on it. Then what happens? If a TO bar bit is also set during power up the procedure, that means once you turn on, once you apply power to your controller itself, that means you turn on your controller. That time also automatically timeout bit, that is a TO bar or TO prime, is automatically set. That means at this time also it makes 0. Then what happens? The WDT can reset this bit TO bar. The WDT instruction reset this. That means it makes TO bar is equal to 1. This possibly happens when the CLR-WDT instruction is not executed periodically. That's it. That's what I'm saying just now. If your controller executes CLR-WDT instruction in regular time intervals, there is no problem in the operation of a controller. If the controller can't execute CLR-WDT instruction in regular time intervals or periodically, what happens is there is a problem in the operation of controller. Then what this sensitive WDT can do is the WDT watchdog timer reset our timeout bit signal which was present in our status register, that is a TO bar is make it as logic 1. Where it happens is CLR-WDT instruction is not executed periodically. If it is not executed periodically, the time watchdog timer send a reset signal to the controller. Then automatically TO bar bit is resets. That means this value is changes to logic 1. So that's the meaning of this. And continuation of this, the normal timeout period of watchdog timer is around 18 milliseconds. This is normal timeout period for watchdog timer. That means your controller must be execute CLR-WDT instruction for every 18 milliseconds duration. If it can't execute it, no doubt your watchdog timer may generate reset signal to the processing unit. Then automatically your controller resets. So that's the meaning of that. The watchdog timer is enabled at the time of device programming, and once it is enabled, the watchdog timer cannot be turned off. When you are programming your device, then automatically your watchdog timer is turned on. Once it is turned on, it cannot be turned off due to any reason. It is a continuously running condition. It is continuously running condition. See here, that's the meaning of this. The watchdog timer is enabled at the time of a device programming and hence enabled. And once it is enabled, WDT cannot be turned off. When you are programming it, you enable your watchdog timer. Once you enable it, it won't be turned off. The same thing also possible. That means once it is a turn off, due to any reason, you are unable to turn on again. So that's the meaning of an X. Similarly, if it is disabled at the time of device programming, the watchdog timer cannot be turned on by any means. That means once you are doing a programming of our device, then you enable the watchdog timer WDT. Due to any reason, you are unable to turn off it. And the same thing, when you are programming your device, once you turn off your watchdog timer, it is not possible to us again to turn on it. That's the meaning of this. And next point is, there is a programmable prescaling is possible with the help of option register bits, that is the PSA, PS2, PS1 and PS0. Just now we gone through that. That is the least significant nibble of option register is very helpful for us to prescaling of both the timer 0 as well as watchdog timer, so that here watchdog timer also supports programmable prescaler option. By programming of PSA bit, we can assign the prescaling values to our watchdog timer with the help of least 3 significant bits of option register. Those are PS2, PS1 and PS0. So this is about your timer's operation in PIC 61/71 microcontrollers, because in those 2 controllers we just identified only 1 plus WDT timers. That means one 8-bit timer circuit, which is our timer 0, and another one is Watchdog timer at WDT. So I hope you understand the timers concept in PIC 16C61/71 controller. In the next class, I am going to discuss about another topic. Thank you for patiently listening.